All right. Hey everyone. So originally the plan for today was to do a Zoom call, but the baby's actually getting discharged today, and there wasn't really a guarantee that I'd be back in time for the 2 p.m. call. So what we decided to do instead is do one video like this, covering the beginning 11.2. Just so we kind of get that out of the way. And then when it comes to Wednesday, we'll continue with the original proposed schedule of doing a Zoom call then, and also on Thursday. Now, there's no class on Friday, right, because it's Good Friday, so their university's closed, so we don't have a Zoom call then, so you get one day off. And then on Monday next week, we will have the other Zoom call, and I should be back by that Wednesday, so we'll proceed meeting in person like normal from that point forward. The only thing we have to try to figure out is how we're going to do. There's supposed to be a quiz for today, which obviously we're doing this video, so that's going to be a little bit different. I'm going to think about how we're going to do that. We might get a little creative. We'll see. So anyways, so at this point, somebody went over all of 11.1 for you guys. So if we kind of recap about that topic real quick before we continue on, that was all about pretty much basic probability. So it started off with sample spaces, which we did before in the previous unit worth of material, where we listed out all the different outcomes of different events, and then we were just listing them. But for probability, right, if we can list all the events, we know how many total events there are, we could then calculate a probability of certain events to occur, right? So for example, if you're doing flipping a coin 3 times, right? There was only one option that was all 3 heads out of the 8. So if I was saying, or asked you the question, hey, what's the probability of getting heads 3 times if you flip that coin 3 times in a row? The answer would be 1/8. Okay, so you started with that, and then obviously as the problems got more complex, right, we couldn't really list them out like we did before, and the same issue happened with all the counting problems, right? So remember from the last unit about those permutations and combinations, right? You can have those similar types of problems with probability, and that's why we cover those first, right? So those counting problems still kind of show up here, but the way we use them is a little bit different, right? Because if I need to count how many total options there are, we can use some counting principles, and we can also use the counting principles to figure out how many options that we are desiring, and then we kind of compare the two, right? Now, fortunately, right, that section started out easy and got a little bit harder, and 11.2 is kind of similar. We're going to do the first 3 pages. Most of it's pretty simple, nothing really too crazy. So luckily this section is going to be pretty nice for you guys. So if you're looking at the note package, it should be page 109, assuming my numbers are correct on here. And to start out with, the main 2 things, well, technically 3 things we're going to cover, is going to be some properties of probability. So there's going to be some facts we kind of need to make sure we're aware of, and it could have been brought up before, but we're going to make sure we talk about them here. And then we're going to do some questions related to them. And then one other major component we're going to be talking about is called mutually exclusive events. And we're going to see what it means to be mutually exclusive versus not mutually exclusive. And then what does that really mean if we're calculating a probability? Like, how does that play into things? And so that's essentially the first 3 pages. So if we're looking at the first 3 pages, I'm going to write out the first 3 properties. So the properties here, so properties of probability, okay, shorthanding that. The first one, this is pretty important, right? A probability is only going to be between 0. So the probability of event E is either going to be between 0 or 1, and it can be either or. Okay, we don't have any answers more than 1, so if you're ever doing a calculation and you got an answer of 2, you definitely did something wrong, right? And if you got a negative answer, still probably an issue. Okay, every probability we answer has to be either bigger than 0, less than 1, or it could be 0, or it could be 1. That's the only 3 options. So to bring that up, right, we can have a probability of an event be equal to 0, and what that means is this implies that it's impossible. Okay, so if we have something that's impossible, we'll say the probability is 0, and that takes care of all the things kind of below what you could get, right? So if I told you, hey, what's the probability of flipping a coin and getting a 2, That doesn't really make sense, right? Because we know a coin typically has heads or tails. So we were kind of dealing with a situation like that. We'd say the probability is 0. And then the third option, which we kind of already discussed, is, what happens if it's equal to 1? Well, it's the opposite. Always true, okay, or certain. So we can say the event is certain or always happens if it's equal to 1, right? So if we say, let's see it's a good one here. Coastal Carolina University is, what's the probability that Coastal is going to be in Conway? Not a really great example, but that's kind of one. I don't want to say the sky's blue because, what if it's raining, then whatever. The grass green, but what if it's wintertime and it's not green, it's dormant, all right? But you know what I mean. So if the event is certain, it has a probability of 1. Okay, so if we're looking at some sort of question and it seems like that doesn't really make sense, that can't really happen, we just say the answer is 0. If we know for sure it's always going to happen, the answer is 1. Okay, and that's kind of the main idea there when it comes to those topics. Of course, I forgot how to move this without making this all messed up. Come on. There we go. All right, perfect. So underneath that, okay, we have an example of a couple different things. So for the example, let's say you're rolling a fair. Now they don't specify this, but we're going to say 6-sided die, not G, 6-sided die. Okay, we have going to be a couple options. A, let's say the number is 3. Okay, so if we say, hey, what's the probability of getting a 3 on a 6-sided die? Well, we think about it and we go, okay, well, how many 3s are there? There's 1 out of how many total options? Well, there's 6. And that'd be by probability of getting a 3. Right? Pretty easy. You kind of did some stuff like that before. But what if we looked at something like this? Other than a 3. So what if I want to know the probability of getting other than a 3? Well, what other numbers are there? We have 1, you have 2, right? 4, 5, and 6. Well, there's 5 of those, okay, out of 6 options, so my probability will be 5/6. Well, let's do another weird one. What if the number was 7? So what happens if I say, hey, what's the probability of getting a 7? Well, you sit there and you go, that's kind of a trick question because there is no 7. And that's right. There's 0 7s on the 6 sides, so the answer is 0, which kind of ties into our properties just talked about, right? We know this is impossible, so we should get an answer of 0. We can also think about it this way. How many options are 7? There's 0 of them out of 6, so you get 0. And then the third one here, what if it's less than 7? So the number is less than 7. Well, there's 6 numbers less than 7 out of the 6 total numbers on the die, so the answer is 1. And this is certain, right? We know all the numbers on a 6-sided die using a traditional, typical 6-sided die. You have 1, 2, 3, 4, 5, 6. All of them are less than 7. So therefore, it's guaranteed it's going to happen. No matter what, this is always true. So the answer is going to be 1. Okay? And that's going to be pretty much how we deal with those type of situations. Now, technically, for part C, or excuse me, not part C, part B, we use what's called a complementary event. Okay? But it wasn't really phrased that way, but the idea is this, right? We know A was getting a 3, and B was technically not getting a 3, right? And what we notice is the answer for getting a 3 was 1/6. The answer for not getting a 3 was the opposite, or the other parts, which were the 5 other numbers, right? So what we can do is if we're trying to find an answer for a problem, and we notice it's a complementary event, we can kind of do some math magic here to get the answer a little bit easier, right? Because if I know the probability of getting a 3 is 1/6, then the opposite has to be the other 5/6, right? So if I was to take the event, so the probability of it happening, and I combine it with the probability of not happening, that's everything possible, right? So think about it, right? You driving to school, either you're going to wake up on time or you're not going to wake up on time. You're going to be in class on time or you're not going to be in the class on time. Either you're going to, get a on the test, you're not going to get an A on the test, right? So when you look at those two events, they're obviously opposites of each other, but there's no other option, right? You're not going to get like something in between those events. So that allows us to do and deal with what are called complements, okay? And it's a little equation for it. It's pretty easy. Nothing too bad. So we're going to look at that equation real quick, and then we'll answer some questions related to it. It's not too bad, pretty simple. So when dealing with a complement, okay, usually complements, we like them because they make us feel good, but this complement's a little bit different. We're looking at two things that combine together to make the whole thing, okay? So essentially, the probability of not E, so E not happening is equal to 1 minus the probability of it happening, right? Which also implicates this. If I take the probability of it happening, E, plus the probability of not E, it should equal 1. Okay, these two things are used together to form this complement rule, okay? This is the probability of not happening, okay? So, some examples we have here is the probability of winning a raffle drawing at a school is 0.0002. What's the probability of not winning? Okay, so if my example was telling me, hey, the probability of winning is that really ridiculously small number, I can use my facts about complements to help me get the answer pretty quickly, right? So, whoops, don't want that. There we go. So for that example, if we're looking at the probability of winning, I'm going to shorthand this a little bit, is equal to 0.0002. What's the probability of losing? That's essentially what I want to know. If I know the probability of winning is 0.0002, how can I find the probability of losing? Well, losing's not winning, right? So if I take 1 minus 0.0002, that'll give my answer. So it'll be 1 minus 0.0002. So your answer would be 0.9998. Okay? Yeah, people like to think they have a chance. They're looking at 0.0002 chance. But in reality, this is the chance of what's really going to happen, right? So that'll be one example of that. Okay, another example we see underneath. We're going to scroll down here a tad. Just got to look at that. Come on, right click. There we go. You're drawing a single card from a 52 deck of cards. So in this example, we draw one card from a deck of 52. Okay. Part A wants to know, this is a standard deck of cards, which you do have available. Okay, if you remember, at the end of 11.1, there is a deck of cards provided on there for you to look at, and there is that list of the dice there as well. For part A, we're looking at the probability that it will be a queen. So we want to know the probability that this card drawn is a queen. So we look at this as, all right, how many queens on there? So if you look at your sheet, you should count up 4 total queens out of the 52 cards. Well, B wants to know what's the probability of it not being a queen. Well, if there's 4 cards that are queens, there are 48 cards that are not queens. Okay, so that'd be the opposite. Now, could you do 1 minus 4 over 52? Yes. Gives you the same thing. Now, if you already know the count here, it's just the opposite, right? 42 plus 48 should be all 52 cards. If the 4 are what you want, then there's 48 that you don't want, right? And since we do not want the queen, we're looking at the 48 that we don't want. Now, get a good habit of reducing. Okay, both of these can reduce. The first one reduces to 1 over 13. Okay, and this reduces to 12 over 13, which, ironically, what's 1 plus 12? Still 13, okay? Just because we simplify doesn't mean all of a sudden they don't add up to 1 again, okay? So if I add these up, no matter if they're base 13 or base 52, these still add up to 1, okay? Very, very important, okay? So that's going to be your complement events, okay? That's based off the fact that the probability of all events add up together should equal 1. So if you have the probability of event happening and the probability of event not happening, they should add up to 100%, always. Now, the second major topic we have are something called mutually exclusive events. Okay, and this sounds really complicated, but these questions are easy once you kind of think about it in the right way. What it means to be mutually exclusive means that they can't occur at the same time, right? So, one thing I guess you can say is, let's think about this here. So if you were to go into like Sino Grill right now and you were to get a drink, I'm pretty sure Sino Grill is exclusively Pepsi products, if I remember correctly. Okay, meaning that you're not going to walk in there and you're not going to find a Coke or a Sprite. Okay, and I'm a big fan of Sprite, but I have to, you know, make a sacrifice and get the Starry, right? But that's because they're exclusively that, you know, drink, right? So what happens is when things are mutually exclusive, we're comparing two things from each other and there's no overlap, okay? There's no outcomes in common. So, for example, something more like in this class, if I'm looking at the results of a coin and the results of a dice, right? I have head, tails on a coin. I have 1, 2, 3, 4, 5, 6 on a die. They're not the same results, right? So those are mutually exclusive events. So sometimes you can be mutually exclusive, meaning that they don't occur at the same time. But there are some times where things are not mutually exclusive, meaning that there is an overlap. And it's very, 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 very important to look at those situations. Okay, because here's the problem. If I'm looking at probability and they are not mutually exclusive, we have like cross-contamination, right? And with this cross-contamination, we can overcount. Because if we're counting everyone in category A and counting everyone in category B, but there's one person that's in both categories, well, I added that person twice. So we have to kind of deal with that kind of issue. So before we can really get into the probability questions with that, we first need to look at, you know, how can we determine if something is mutually exclusive versus not mutually exclusive. Okay, and really the idea is just looking at, does it happen at the same time? If it's yes, you're not mutually exclusive. Okay, this is kind of the interest people up. If they can occur at the same time, then you're not mutually exclusive. If you can't occur at the same time, then you are mutually exclusive. So there's a little bit of a backwards thing there. Okay, it's a small nuance that you kind of need to keep track of. So looking at the examples here, part A, you're picking a spade and a diamond, a deck of cards. Well, if you look at the deck of cards, right, every card has a suit, but there's no card that's both of those options at the same time. So we'll say that is mutually exclusive. I'm fine if you write ME for short, because you'd be writing out that word or that combination of words a lot. Let's look at part B. Picking a diamond and a queen from a deck of cards. Okay, so if you pick one card and it's a diamond and a queen, can that happen at the same time? And the answer is yes, right? There is exactly one card in the deck that's a queen and a diamond simultaneously, meaning that these are not mutually exclusive events. So if I was doing the probability of A, it's going to look a little different than the probability of B because we have this cross-contamination with B. Okay. For C, rolling an odd number and getting a multiple of 3. Okay, so if I roll a die and I look at the number on it, can I be an odd number and multiple 3 at the same time? Well, the multiples of 3 in the die are 3 and 6. 6 is even, but 3 is odd. So this is not mutually exclusive. And then for part D, getting an odd number and an even number, right? So is it possible to have an odd number and an even number at the same time? Nope, that doesn't make sense. So that'd be mutually exclusive. Okay, and these are the results of that question. Okay, it's a very easy question to answer, and it's really based off the one question: can these happen at the same time? Depending on how you answer that question is going to dictate how you say if it's mutually exclusive where they can't happen at the same time, or not mutually exclusive where they can happen at the same time. Okay, so you got to be a little careful with that. It is a little backwards. Okay, so some people don't like that, but that's just kind of how it rolls. Okay. Now, you're probably thinking, okay, those questions aren't too bad, but Mr. McCary, when does it start getting hard? Well, what happens is when we're trying to answer these questions, there is a little bit of an issue we have to worry about. Okay, and that issue comes into counting. Okay, so before we get into like the specific questions for that, let's look at what's on the next page. So looking at the top of page 111, there's two things I want to do here. Okay, so this example, you're drawing a card just like that other one. Okay, so in this example, we're drawing one card. Whoops. I hope if I can spell draw right. You draw one card, and then for A, okay, part A wants to know what's the probability that the card would be black and a 2, right? So how many cards in the deck are black and also 2 at the same time? Well, there's 2 of them out of the 52, meaning it's 1 out of 26, okay? And then for part B wants to know what's the probability of it being a heart and a diamond. Okay, so we want the probability of being a heart and a diamond. Okay, now we talked about a similar situation, okay, like this before, right? So like part A for the previous one, we compared being a diamond and a spade, and we said that can't happen at the same time. Well, guess what? It can't be heart and diamond at the same time, so this is going to be impossible, so that's 0. Okay? So sometimes mutually exclusive can work in this way, where you're looking at an AND example, where you're kind of like looking at them together, and if they are mutually exclusive, the answer is always 0, because they can't happen at the same time. If I know I'm dealing with two different topics that are not mutually exclusive, we do have at least some answer that we can get. Okay, and the reason why we covered these is our formula here in the bottom of the page, or mid-level of the page, is dealing with 3 things. We're dealing with probability of A, B, and then A and B at the same time. Okay, so if they are not mutually exclusive, we do have a number that could be placed in that A and B slot. Okay, but if we know they are, if we know they are mutually exclusive, then we say that number is 0. Okay, so we're going to kind of look at that formula, talk about it a little bit, and we'll do at least 1 or 2 examples with it. We won't go in super depth, but I do want to at least brush the surface, get your brain thinking on it, see, how you feel on it, okay? Before we get into Wednesday. So, this is one of the most important, not the most important, but it's a very important rule we cover, which is the addition rule. So it's the addition rule of probability. Okay, so the way the addition rule works is it deals with A or B scenarios. Okay, so sometimes you're dealing with things in life, right? You either have option A or you have option B. And the problem with that is, depending on if they're mutually exclusive or not, the answer could get a little complicated. If these options are mutually exclusive, then it's pretty easy. We just add the probability of both and we move on. If they are not mutually exclusive, meaning there are options in A that also show up in B, we have a counting issue. Okay, we can overcount. So the formula is this. Okay, so it's probability of A or B is always going to be equal to the probability of A by itself plus the probability of B by itself. But since we could be counting items in A and B simultaneously, we minus off the overlap, which is the probability of A and B. Okay? If the two items are mutually exclusive, then this A and B would be equal to 0, and then we're just left with this first part. But if they are not mutually exclusive, there is a number that has to go in here. Okay? So the reason why we did those scenarios with it being mutually exclusive or not is because you have to make that determination when using this addition rule. Okay? So an example to kind of showcase this, we look underneath. You're drawing a single card. So we draw one card. Okay? And what we want to know is what's the probability of that card will be a king or a diamond. Okay? So, if we think about it, right, can we have both these things happen at the same time? Well, yeah, there's one card that's both a king and a diamond at the same time. So if I do the probability of this, okay, what this will equal would be the probability of getting a king plus that probability of getting a diamond. But we also have to minus off that probability of getting both. Okay, so king, 4 out of 52, right? 4 kings in a deck out of 52 cards, plus we have 13 diamonds out of the 52 cards. This is the one thing people don't remember a lot of, right? There's 4 kings, but there are 13 diamonds. But we did say that there's one card in that whole deck that satisfies both conditions at the same time. And the reason why we set up this way is because if I count all the kings separately and all the diamonds separately, this king of diamonds is in this group of 4, but he also shows up in this group of 13, right? So the problem is if I just do 4 plus 13, I counted that king twice. So I had to minus that one extra count. And that's why the formula works this way, okay? We add up both conditions individually. We hope there's no overlap, but there are a lot of times we do have overlap, right? Not everything is mutually exclusive, right? There's a lot of things that are not mutually exclusive. So we have to worry about running into those scenarios and making sure, hey, you know, if it's mutually exclusive, what happens? Well, if it is, then this ending here, the minus part, doesn't exist, right? And that's what it has right in there, right? If A and B are mutually exclusive, it's in bold, then probably A and B equals 0, right? There's a bunch of stars there right underneath the rule, okay? That's what you do if you know that is a fact, okay? In this example, we knew it was not mutually exclusive, so we had to worry about that answer. Now, we'll do one more. There's one more on the page. We'll knock that one out, okay? If you're thinking, if the first example was not mutually exclusive, I wonder what the next one is. If your guess is that it's going to be mutually exclusive, you have pretty good intuition because that's what's going to happen. But let's look at it. So you roll a die. Okay, 6-sided die. We want to know what's the probability that the number on the die is a 2 or some odd number. Okay, so you roll a die one time, but you're okay if the number's a 2 or some sort of odd number. Now, obviously, right, we talked about this before, 2 is not an odd number, right? This is definitely an even number. Now, 2's prime, right? It's an even prime number, but that's irrelevant, okay? 2 is even, not odd. So if I roll a 2, I'm not odd. So these two things can't happen at the same time. So when I do this answer, there's only 2 parts. Hey, what's the probability of getting a 2? Plus the probability of getting an odd number. Okay? Well, how many 2's are there? Well, there's only 1 out of 6. Well, how many odd numbers are there? Well, there's 3 out of 6. So if I have 1, 2, and 3 odds, there's technically 4 options that we're cool with, right? So we get 4 out of 6, which we can reduce to 2/3. Okay? Oh, I just realized I didn't answer this question. I didn't finish this one. Yeah, for the deck of cards, for the king, diamond, and probably the king or diamond, we do 4 plus 13. That's 17 minus 1. You get 16 out of 52. Okay? Got so excited about the mutually exclusive stuff that I forgot to write this down. Okay? And let's see, 16 out of 52. That should be 4 out of 13. So reduce down to 4 over 13. Okay? So we can kind of compare the results, right? If they're not mutually exclusive, extra problem, extra piece in the equation. If they are mutually exclusive, then we don't have to worry about that, right? So here they were mutually exclusive. Okay, so we do not have that part. But this was not mutually exclusive, so we had to worry about this extra piece right here. Okay, so you got to always check into that. All right, so that's the first 3 pages. There's 3 pages left going in more detail on those or situations, but we're going to kind of put a cap on it for now. Okay, I think you suffered enough, right? Too much math. So again, we're going to continue with the Zoom call as originally planned for Wednesday. Okay, but I want to get this video out to you so you still had something for Monday to do and kind of stay on track. And then on that Wednesday Zoom call, I'll give you an idea how we're going to do that first quiz. Now, the first quiz was going to be on 11.1, and then the stuff with fractals, which was, I'm trying to remember what number that was. It 9.8? Let me see. Yep, 9.8. So there's going to be kind of some questions on fractals and some questions on the basic probability. Okay. I'll let you know exactly how it's going to look like on Wednesday in the Zoom call, so make sure you're there for that. Otherwise, if you have any questions on some of this stuff, definitely let me know. Definitely try out some of these questions on the online homework. Now, obviously, we haven't finished this thing, so there could be some questions if you're looking at the online stuff that might be a little complicated. If you want to try it yourself, go ahead and do so, because we technically covered the concept, but there's some technicalities you can run into, so I definitely want to cover more examples to make sure we're comfortable with that before you go fully diving in. Okay? Again, if you have any questions, let me know. Otherwise, see you on Wednesday.